Okay, thank you. So this is my lecture 4. This is the introduction to GUI method and applications. So uh, so today I'm going to talk about parabolic GUI, the inner outer GUI scheme in the non-alto case, and the non-alto case. So yesterday we talked about the parabolic GUI in the alto case. And we apply this parabolic GUI to this energy critical Fujita equation. And we take dimension 5. And so P is 7 over 3. And we construct a blob solution with this blob profile, with this scaling parameter. And we achieve this by the inner outer GUI. So the idea, so let me just go over this again. So we take our Orban Tanati bubble, we add a linear solution to the heat equation, and then this will account for the initial data. And then the phi is the error. So the remainder, the phi consists of inner part and outer part. So this inner part of phi, eta phi, and outer part of psi. So in the inner part, you use the rescaled variable, x minus psi over lambda. And so this is a simplified inner outer GUI. So the inner problem is the linearized parabolic problem and with nonlinear terms, but only in this region where x is less than 2r lambda. And the outer problem enters into inner problem by this user p minus 1%. The outer problem, which is solved in the whole space, and from T to capital T, it connects all the remaining error, and the inner problem enters into the outer problem by this cutoff function. So the key observation, as I mentioned yesterday, is that in order that the inner outer decouple, we need to estimate the outer to inner. This is the outer to inner and inner to outer. The inner to outer only occurs near the boundary. So for the GUI to work, we need to find an inner solution which has a fast spatial decay and a fast time decay. And the basic idea is to develop a sort of freedom alternative sort of existence theory for the linearized operator. So for the linearized operator, we want to construct a solution if the right hand side has a time decay and space decay. We want to find a solution phi and Caesar. Caesar is also part of our solution, so that phi also decays uh, space, spatial decay and time decay. And we achieve this by blob argument. And we have, by blob argument, we're going to see two negative problems. And we're going to see a ancient solution for the linearized parabolic problem with the orthogonality condition. And the second limited problem is the Asian solution for the heat equation with isolated singularity. So by excluding both cases, and we get our uh, our upper estimates. Then from the upper estimates, we get existence. So in this blob argument, the fact that this JJ or this kernel in L2 are very important, because otherwise we cannot take a limit inside. So we cannot, and we cannot get any contradiction. So 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 today I'm going to talk about the non-alpha case, the dimension 2, 3, 4. So let me start with the dimension 4. So the main result I'm going to present today is the following result, which I prove with the pillar Musso and Yifuzhou. So I assume that n equals 4, so the critical exponent is 3 for each small time. We can find initial data such that the solution blows up at exactly at this Q, and the blob at the main order is like the Orban-Tonanti bubble. The blob rate L infinity log is like log square over t minus t, or one or lambda, or the scaling is t minus t over log square. And this blob is almost generic coordination 1 stable. So, and immediately we see a difference between dimension 4 and the dimension 5, because here our blob rate is a little bit different. It's no longer algebraic, and there's a logarithm correction here. And again, let's assume a regional symmetric. Okay. Okay. So, uh, let's do the proof, and then let's see where the problem is. Okay. So we go back to the answers we did yesterday. So we take the Orban-Tonanti bubble on the plus 0 with is a solution to linear heat equation, and we compute the error. And the error we compared yesterday consists two parts. The first part, which is the data, is the heat equation, the heat initial data. This comes from the initial data, and this comes from the UT. So if we rescale x equals lambda y, and our error will be p lambda minus 2 u to the p minus, here p is 3, and n equals 4. So we get this. And the last term is the scaling parameter. Okay. So in dimension 4 and the p equals 3, and both u and the zn plus 1, the scaling parameter decays like 1 over r squared. So immediately we see a problem. Even from the beginning, we see a problem. The problem is the error is not L2, because this is just 1 over y squared. So, of course, if the error is not L2, you cannot do any L2 theory. You cannot multiply both sides by L2 function. So we immediately we if this is not L2, this will destroy any solvability theory. In fact, this one is 2. 2 is dangerous for any elliptic theory. To get a decay solution, we need 2 per sigma. So we need to correct this one. So even from the beginning, we see a problem. Okay, and then the second problem is the slow decaying kernel. So this kernel is not in L2. This one is not L2, and so you cannot use any orthogonality condition. You cannot use any orthogonality condition. So let's now correct each of these problem. Let's try to overcome each of this problem. First, let's look at the slow decay error. So this error is a slow decay. So this means I need to add a term, to get rid of this one. And so we go back to the original variable in x. If we go back to the original variable, this term becomes like number prime over u, over lambda square plus x square. So, and what we need to do is correct this term with a global term. We have to correct this not pointwise, but a global term. So the idea is to solve the heat equation with this right-hand side. And the solution to the heat equation, we have to choose a very special solution to this heat equation. And the solution to heat equation, this is how we choose. We choose this in a self-similar form, and uh, uh, and uh, uh, the reason that we correct this, and and because we want Pfizer to decay at infinity. So the global correction is very important. I don't have time to discuss this because this term, this global correction determines the Brap rate. Okay, determines the Brap rate. So now we add this global term to the initial approximation. So we have u lambda 0 and phi lambda 0 and plus process 0. So the new area now has a fast decay because you get rid of the slow decay as a fast decay. So and and uh, we need to compute the global non-local term. Now this global non-local term is, if in initial case, if in the initial case, this is very familiar to people who have been working on elliptic grooving construction. Because what is this global term? This global is nothing but the projection of this bubble in the heat equation. Is this is just the projection? So what we're doing the projection of the heat equation in the heat equation, and so this is how why we have this global term. Okay, so we deal with the slow decay, right? The slow decay term now. So next is the main problem is to deal with the slow decay kernel. So kernel is not L2, and we cannot use L2 theory. We cannot use L2 theory. We cannot use Brown. So we go to the inner problem, and we will scale the time variable as before. And so in the inner variable, the approximate solution looks like this: one over one plus y square. And so the inner equation is like phi tau plus equals Laplace phi plus 3u square phi plus the error term plus 3u square. We have this global term, correction term, and we have this coupling term. Okay, and there are other nonlinear terms. So we will call all these terms are called, let's call H. Okay, all these terms let's call H. So and the outer, this is the outer problem. So the outer problem, we have the cutoff function. We have the cutoff function. Again, so outer to inner is this, and inner to outer this. Okay. So uh, the inner to outer only happens near the boundary of BR. Okay. So what we need is a solution that decays near zero, near the boundary. The solution inside may be large. Okay, inside in the water one region may be large, but after a while, when you go to the boundary, go to BR, it decays. So, so this is the key. As the inner solution we found grows large in the interior, but decays only decays near the boundary. Only decays near the boundary. Okay, so this is the linear theory that we're going to present. We assume radial symmetric, so because for the non-radial mode, they are L2. The kernel is L2. We can use the L2 theory. So the main vision problem now is the mode zero, is the Z5, which is the radio mode, which is the scaling one. Okay, so this is the problem. This is similar to n equals 5. And we assume now the decay, the error decays like in time and decays in space, 2 plus sigma. Okay. Then what is our result? Our result is following. Then for sufficiently large R, okay, so R is large, there exists a solution to this problem, phi and C0, such that phi is like the following, like you still have the time decay. Let's look at the phi. Is R to the 4 minus sigma log R 1 plus y to the 4. Okay? So if y is order 1, phi grows like R to the 4, almost like R to the 4. Okay? So this is really big inside in the or in order 1 region. But when y is close to the boundary, when y is R, this one is R1, R to the 4, this R to the 4. So it decays, they have a little bit decay, which is R to the minus sigma. Okay? So this is the character of the non-L2 case. The solution we're going to build is big inside the inside in the interior, but near the boundary, near y close to R, near the boundary, it decays literally. Okay, so this is the linear theory that I'm going to present, and okay, so let us now assume we have this linear theory now. Let's see how the inner outer works. So we assume that we already built this solution for the linearizer problem. So in the inner region, when y is order 1, phi grows like R to the 4 minus sigma log R, which is extremely big. And near the boundary, phi decays. So this is the good part. Okay, this one is the good part. The phi decays. Okay, uh, near the boundary. However, the first term creates huge problem for nonlinear terms. Since we have to take cutoff far away from to get a regularity, because we need a regularity for the outer problem. To get a regularity for the outer problem, the cutoff is far is it should be, you want to gain regularity, you want to gain decay for this term, you want to gain decay, and then it's better you cut as far as possible. Uh, but then there's a problem, because the optimal region we can take, there's a balancing between the outer problem and inner problem. The balancing problem is R is tau to the 1/3, which is small still under the subsimilar. The subsimilar region is square root tau. But this is huge. You see that if you're in the interior, this will lose tau to the 4/3. So it means you lose a lot of time decay. Okay? And so, and this is a huge problem that to decide which tau to take, which R to take. Okay, this is the whole, and to correct this, we have to do a secondary reduction. But I will not discuss this, because this in the inside, this is too huge. Okay, this lose a lot, too many derivatives. Okay, so let me now present the linear theory, for the non-L2 case. Okay, so let me just repeat the result. We have this fast decay kernel, and fast decay the right hand side, and is orthogonal to Z5 to the scaling parameter. The solution we get has loose R loose R to the 4 in the interior, but decays near the BR like R to the sigma, 1 over R to the sigma. So this is the linear theory that we're going to prove now. Okay, so we're going to do this in 3 steps. Okay, so now since we cannot use the L2, this we cannot use the L2, but we can still use the elliptic theory. So given this edge, this edge is given, this edge, I can solve the elliptic first. Okay, so I solve the elliptic, and for the elliptic, we don't need L2 theory, right? For the elliptic, you can use D12, to solve. So for the elliptic, as long as the right hand decay fast, then you can have a solution that's called H, which satisfies, which decay in space. Okay, y to the sigma, tau to the minus. So here, tau is fixed. In this one, tau is fixed. Okay, so we can solve this problem by elliptic theory, because in the elliptic theory, we don't need L2. We can use D12. Okay, or use other space. So elliptic problem we can solve. We get a elliptic solution. Okay. So this is our first step. We get this elliptic solution, and the elliptic solution decays in space and in time. Okay. So in the second step, we solve. We put the edge, the big edge on the right hand side. This big edge is the one from the first step. Okay. We put the big edge on the right hand side. Okay. And so this one only decays like 1 over y to the sigma. So very slow decay. Very slow decay. Now, for this problem here, we will solve this problem with differential boundary condition. Okay. Phi r tau equals 0. So we solve this with differential boundary condition. And we assume that phi is orthogonal to the unstable mode. This we can always do this because this unstable mode is exponential decay, has an exponential decay. So this orthogonal condition is okay. And we start with the initial condition 0. Okay? So let me repeat. H is the elliptic problem. Is the solution from the elliptic. Okay? Solution from this H, lead to H, we solve the elliptic. And we take this new solution, and now we solve the linear parabolic with this. And we don't expect phi to decay or something, because this H only decays like 1 over y to sigma. And also we don't expect that, there should be many solutions to this, but because I put the differential boundary condition, so the solution is unique now. So, and what I want to claim that for this problem, the solution for this problem, we have the following estimate. Is tau to the minus mu, r to the 4 minus sigma log r, and 1 plus y square. Okay, this is the main estimate we have. Okay, this is the main estimate. So So this problem here, you don't expect the solution to have decay for this problem. Because for example, if H is constant, and then you get a solution which is like R square, big R square minus little r square. So you don't expect the solution to decay. Okay? So this is the main the estimate, okay, with the differential boundary condition. So why do we put the differential boundary condition? Okay, because we want to obtain some L2 estimate or some quantitativity. Okay, so this is the key step. Suppose I've already done this step. Okay, so this step is done. Then when problem is solved. Okay, why? So our solution will be I just take the L0, which is the elliptical operator. This is L0. I take L0 phi, big phi. I take L0 big phi on both sides. So get L0 big phi, L0 and L0 square and big phi, L0 H, and this L0 L Z0 is lambda Z0. So 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 the new solution, the little phi, which is the L0 phi, satisfies phi tau equals enough L0 phi. Okay, this is L0 phi because L0 H equals little h minus h, right? So you get this plus h, and with this, the mu zero, and this L0 phi, since you are taking two derivatives in big phi, you're taking two derivatives in big phi, so formally you get 1 y to the 4. Okay, and this proves that this is exactly the solution we have constructed for mode zero. So the three steps. The first step is very simple. It's elliptic. You use an elliptic theory. The main problem is the second step. In such step, you don't impose any orthogonality condition. There's no orthogonality condition on the kernel, and you want to find a solution, okay, with the differential boundary condition. So once you found this solution, you just take L0 of this solution, and this will solve your original equation. So the three steps are very easy to do. Now the only problem is problem 2. How to find a good solution for this problem without orthogonality? Okay. Now this big H, we don't assume any orthogonality. There's no way we assume, and this big H actually is only slow decay, only slow decay. So this theory we call a linear theory without orthogonality condition. Okay, so you say that this linear theory without orthogonality condition, you lose r's to the 4. Now even near the boundary is like r square, so you lose a lot of r's. If your linear theory, if you don't have an orthogonality condition. So the main problem is now this step 2. So let's try to prove this is step 2. Okay. So this is a linear theory without any orthogonality condition. So the estimate are very bad, but it's good for our use. Okay. So this is our H, big H is like this, and the solution we get, we lose, is basically is like R square. Okay, R to the 4 over Y square. This is how we built this solution. First, let's concentrate the error. Okay, this H only decays like 1 over Y to sigma. And so let's first concentrate the error. So what to do is we solve this parabolic problem. We cut the U square in some big number, a fixed big number, and if we cut this U square, uh, then this operator here satisfies the maximum principle. So we are able to we don't need any orthogonality condition. So this problem can be solved. We can just use barrier, okay? And this Laplace plus 3u square 1 minus eta satisfies maximum principle because the scaling kernel changes sign only once. So so you have maximum principle for this. So by barrier, this solution will be tau to the minus mu and r to the 2 minus sigma because your solution here only decays like 1 over y to the sigma. Okay, so basically you are like solving a Laplace equation. Laplace equals this, so you get this phi 1, and then the new you set phi because phi 1 plus phi 2, then phi 2 will satisfy the linearized problem, but now this will have faster decay now because of the U square, because you cut this, right? You cut this, so this one will have faster decay, and the new area will have faster decay, and we can adjust so that this is orthogonal to Z0. Okay, so now uh, we have uh, a solution that we need to study this phi 2, and this phi 2 has a faster decay, and now we need to understand what is the upper estimate phi 2, upper estimate for phi 2. Okay, so to get upper estimate phi 2, we don't just do as in the parabolic. Now we use L2. So we multiply both sides by phi 2, and we get this energy estimate. And this is a well-known energy. This is the the usual classical energy estimate. So you get the d tau and the L2 square equals gradient plus gradient phi square 3u square phi 2 square equals this. Now this is the dimension for now this guy here, because I assume the phi 2 is orthogonal to the unstable eigenfunction. So this guy should be uh, should be non-negative, okay? Because phi 2 is this should be big phi 2. Phi 2 is orthogonal to the unstable eigenfunction. Now, since the dimension is 4 and the phi 2 equals 0 on the boundary, and we can show that we have a lower bound, a spectrum gap for this projective form, but the spectrum gap loses r squared log r. Okay? It's like r squared log r. So, and this is where we use the division boundary condition. Right? This is division boundary condition. This is how we use the division boundary condition. So using the division boundary condition, we can gain a little bit spectrum, but the spectrum gap, but spectrum gap depends on R square. Okay, and then you use so this one you get 1 of R square, and then use the ground hole inequality. Then we can get the L2 estimate also lose R square, and the L2 estimate lose R square, and by using the standard elliptic theory, uh, and we get the L infinity will lose like R to the 4 log R. Okay, so this in any final region, in the final region. Okay, but then this problem here, after some final region, say R greater than 10 or some, this satisfies maximum principle. I can use maximum principle when R is greater than 2 or 10. Okay, finite. Okay, sorry. So, and so that's how we get this R to the 4 log R, how this R to the 4 log R come from. And so outside we can use the maximum principle, and we can use this barrier, so we get R to the 4 and R square. And you combine phi 1 and phi 2, you get R to the 4 and over 1 plus R y square. And this is the whole proof. Okay? So, and this is the proof of the step 2. So in the so the step 2 is the linear theory without orthogonality condition. For the linear theory without orthogonality condition, we use the differential boundary condition. So we do 2 steps for step 2. First, we concentrate the error phi. First, we concentrate the error, and then we use the Guanghuo energy estimate and the Guanghuo inequality, and using the spectrum gap. The spectrum gap depends on R. Using the spectrum gap, and we get L infinity estimate, which in the interior, which is loose like R to the 4 log R. And but outside we use for outside the finite region we use the maximum principle, and we get this this decay like y square, and all together we get the desired estimate. Okay, so this argument has been used in many problems, in like Kindersiegel, in Harmonic map, in lots of problems. As long as your problem you don't have L2, your kernel is not L2, you can use these 3 steps and to get a linear theory. Okay, so so this linear theory, as I said, is barely good enough for the 4D problem because you lose too many R's. And we can have a linear theory with less loss of R. We can just lose like R to the sigma, but this is called secondary reduction method. Okay. So I will not discuss this. So now, so once we have the linear theory, and suppose we choose a good a suitable R, we have to choose a suitable R, and then our last step is to justify the C so that the Lagrangian multiplier equals 0 in the infinite dimensional reduction in the infinite dimension. So in the infinite dimensional reduction. Okay, so in the end, we need to solve this will contain the dynamics, and and from from this, what we get is this kind of dynamics. This is a non-local ODE now. So unlike the dimension 5, dimension 5 is lambda dot equals lambda to some power. But in the dimension 4, our dynamics is a non-local ODE. So it's integral from 0 to, you can take it from 0 to t minus lambda square t, and the lambda dot over t minus t, and equals the right hand side, equals this. So now the question is how to solve this non-local ODE. So this is the non-local ODE we need to solve. And again, we have been struggling with this non-local ODE for a while. And the reason is that this non-local ODE, I mean, of course, one want to take out the number dot t, and then then solve this. And the problem is that this kind of terms is good in L infinity if you assume lambda dot is holder, but it's not good for holder. So, what we do is the following. We decompose this into t to t minus t, capital T minus t, and from little t to t minus t to t minus lambda square, and we take out the lambda data t, and we have this remaining term, and this first term, we can assume t is like capital T, and this term we can just leave like this, and this is the term we're going to say this is a small, will be a small term, but you lose the regularity. This term you lose the regularity. So the needed water term will be these two terms, and for these two terms, and we found that there's OD to solve, and we found the lambda is like t minus t over log square. So what about this term? The full solvability of a reduced problem is rather delicate, since this term lose the regularity. So if you put this term in the reduced problem, you lose the regularity. So means if you want to get L infinity estimate, you need C alpha estimate. If you want to get C alpha estimate, you need C2 alpha estimate. So you cannot solve the problem. So, and here comes the idea is we put this term in the part without orthogonality. Remember, we have a theory with no orthogonality condition, without the orthogonality condition. So we're going to put this term in the part without orthogonality condition, and then we do the inner outer green. Okay, and we gain some regularity here. So this is a very delicate. So to solve this problem, since I don't have time to discuss this. So in dimension 4, the reducer problem is also different from dimension 5, because the reducer problem is a non-local ODE. It's a non-local ODE. Okay, this is dimension 4, and for dimension 3, the construction of finite time block is a little bit different from dimension 4. In the following sense, for the outer problem, we're going to take a special solution to the heat equation, and they are self-similar type solution for the heat equation. We we use the self-similar solution for the precise zero. We use a self-similar type solution for the precise zero, and we use this self-similar solution to match the inner problem, and our block rate is t minus t to 2 times k. And for the inner part, you do the same, and the idea is now is how many R's you lose. Here in dimension 3, unfortunately, you lose a lot of more R's. You need R to the 4 minus sigma. And this is a huge problem. Okay, this is a huge problem in dimension 3. And the reduced problem is also non-local. And for this non-local ODE, we use the Laplace transform to solve this problem. So this is the dimension 3 case. Okay, so we talk about the parabolic going for dimension 4 and dimension 3. So dimension 5 and 6, there's an alpha case. Dimension 4 and 3, there's a non-alpha case. So what about dimension 2? So in the dimension 2, the critical equation is Newell. So if you consider ut equals Laplace plus e to the u. So if for the Newell, we have this standard bubble, which is log. So you linearize around this standard bubble, and you get this linearized equation in R2, and with the parabolic. Okay. Now in this problem here, we need a good linear theory to solve. Now this problem is worse than the other in dimension 3 and the dimension 4. And the reason is that this kernel here, so you have the translation kernel, which is L2, which is not L2, and the Z0 here, which is just bounded. So you have a kernel which is just bounded. So for the translation mode, we have some decay. So we can use the non L is not L2. We can use the dimension 4. Like this will be like a dimension 4. Now for the scaling parameter for region symmetric case for this kernel, the non L2 does not work because the operator far away is a 2D operator because this is very small. So it's a 2D operator, 2D Laplace operator, and we cannot expect any special decay uh, for the 2D heat equation because this is a Laplace equation. So for Laplace equation, you don't expect you get a decay solution. Okay. So to overcome this problem, for the mode 0 case, for this case, we use a new method, and this is called distorted Fourier transform and DFT. And I don't have time to discuss this here because this I will need a lot of time to discuss this distorted Fourier transform. And you can this is the reference for distorted Fourier transform. Yannick, myself, and Juncheng and Yifuzhou for the H system. So 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 the takeaway is in dimension 2, uh, with the Newell type non-identity, we can still do parabolic green, but the parabolic green will be uh, quite non-standard. Will be the distorted and the Fourier transform. We need to use the distorted Fourier transform to get all the estimate. Okay, so this is an overview of the non the parabolic Gaussian, and in all this, so we discuss parabolic Gaussian in dimension 5, and which is L2 case, and dimension 4, 3, and 2, that's a non-L2 case. And in all these discussions, we construct solutions. Okay, yeah, we construct solutions. In the remaining part, I will discuss the application of the parabolic Gaussian in analyzing the block solution. And this I called reverse parabolic Gaussian. And the reverse parabolic Gaussian only works in L2. Okay, and so this in the last part of the this lecture, I will discuss this reverse parabolic Gaussian, and so this parabolic Gaussian is not just to construct solution. You can use this Gaussian to analyze the solution. So the main theorem we want to prove is the theorem I mentioned for n greater than 7, and when p is critical, u is positive. We don't have any energy constriction, energy restriction for u, and we prove that all blobs are type 1. So there's no type 2 blob if u is non-negative, u is positive for n greater than 7. So here we don't assume any energy, any is user is just bounded, okay? And so we prove that all blobs are type 2, type 1, and we don't have any energy energy restriction. So how to prove this? We prove this by reverse parabolic gradient. So we're going to do analyze the solution. We're going to do the gradient, but in a reverse way. We already have a solution, and we want to see the solution actually has inner and outer part, and we're going back and to find the dynamics. So this is the reverse parabolic gradient. So the restriction for n greater than 7 is the following reason. Uh, is that the scaling parameter, as we discussed in the last lecture, formally the scaling parameter behaves like lambda to the n minus 4 over 2. So if n greater than 7, this number will be greater than 1. Okay? And so this means you have Lipschitz nonlinearity. And so we have a Hanukkah inequality. Now, if n equals 5 or 6, still L2, but then we don't have the Hanukkah inequality. Then we have a global equation. So what is the difficulty in proving this theorem? First, we only assume L infinity. So there's no energy bound. So the number of bubbles can go to infinity. So we approach the block time. So we approach the block time, you have infinite, maybe for each time t, you have finite number of bubbles, but when t goes to capital T, this number of bubbles will go to infinity. So this is the first difficulty. So we don't have the energy bound. And the second difficulty is that we don't assume any shape of the bubble. So we may have bubble tower, and we may have bubble cluster, and inside the bubble tower we may have bubble cluster. Inside the bubble cluster we may have a bubble tower. So the bubble tower and the bubble cluster, they're all mixed. Okay, and we have to understand how to get the dynamics for all these situations. Okay, and the third difficulty is, even if there's one bubble, the outer problem here in our construction, we assume the outer problem is L infinity, but we do the analysis. You cannot assume the outer problem is L infinity. So the outer problem may be a type 1 blob. And this is exactly happens in dimension 6. In dimension 6, the outer problem is type 1. So and we have to show that this outer problem actually cannot have type 1. Okay? Cannot have type 1. So so uh so how to prove this? The reverse bubbling, we use the energy concentration. We exclude the higher multiplicity case, bubble tower and bubble cluster. And so this is a parabolic compactness argument for Yamabe problem. For the Yamabe problem, there's an elliptic compactness argument by Sean and Yannick and other people. Here we use the reverse parabolic gradient to do the parabolic compactness argument. And the last element is the parabolic second order estimate, and this is a reverse in the outer parabolic gradient to exclude the multiplicity one case. Okay, so in the elliptic case, I mentioned that we use the reverse elliptic gradient and to show the C2 alpha estimate for the nerve set convergence of nerve set from C1 alpha to C2 alpha. And there we use the elliptic refer elliptic green. Here we use the parabolic green. So, okay, so what is the roadmap to the proof? So we assume by contradiction, there's a type 2 blob. We determine the possible blob profile, the blob analysis, and the energy concentration. So, and we show that, as I explained at the beginning, that the type 2 means that inside inside the bubble, UT is much smaller than Laplace. So it's like elliptic problem. And we determine the dynamic law for the bubbles. We use refined blob analysis, and we use this reverse parabolic green, the inner outer decoupling. Okay, so let's now do the proof. Suppose we have a blob point, and we need to analyze the first bubble, okay? And so determine the blob profile, we zoom in, okay? And using the scaling invariance of the equation, and we, because this is a critical exponent, so division norm and this norm are invariant. So we have a parabolic phenomena. But this is a subcritical case because our we have one more variable, which is ut. So first, we decompose the bubble into into this L1 measure and plus the singular measure. And the main problem is to analyze the singular measure. Okay, and the proof of this is from the Montes formula of Giga and Kohn. Okay, and so once of this, then by Stewart's global compactness theorem, for almost all t at each time t, we can have this bubble tree decomposition. This is a standard Stewart decomposition. So at each time t, we can do a Stewart decomposition. So this Stewart decomposition says U can be decomposed into a regular part with U infinity plus n of t of this bubbles, okay, and the little o1 is a small in h1 norm. So here, because we assume it's a positive solution, so the bubble is a positive bubble. And here, the positive bubble will have the classification of a Caffarelli Gatorson spark. Okay, so this is a very nice formulation of the Stewart decomposition, but unfortunately, it hides many difficulties. There is, and inside this Stewart decomposition, you can have bubble tau. So bubble tau, this is in the last part of my lecture, yesterday, I discussed the bubble tower. So in the bubble tower, all the centers are almost at the origin, at the same place, and one bubble on the top of the other bubble. And this is the bubble tower. And we have the bubble cluster. The bubble cluster means the bubbles are separated, okay, by the scaling. And so this bubble tower indeed they exist. So we need to exclude this bubble case. So this is the bubble tower, and this is the bubble cluster and the bubble tower. Okay. So we need to understand. We need to show that all this cannot happen. Okay. All this bubble tower, bubble cluster, and all this cannot happen, and we should only have one bubble. Okay, and first we use the tangent plane analysis, and we get the limit. Okay, we get the limit. We get a bubble tree. Now, Let's suppose we have just one bubble, and we need to understand how close is UI to these particular bubbles. So through decomposition, give us very nice decomposition, but all the enemy, all the information is here, is on this part, need O1 and this one. We need to understand what is the need O1, what is the next order. And so how close is UI to the particular bubble? So the next order is the most important. The next order determines if a type 2 blow bulb should exist. And modular these parameters we can get we can use D12 and we can or H1 we can get optimal approximation of the Sire bubbles, okay, and this gives us also orthogonality condition, and which leads to reduction for the modulated parameters. And so we need to understand the remaining term, and because the remaining term is determined, the error function is determined by the interaction between bubbles and the background and interaction between different bubbles. And we see this in the last lecture. In dimension 5, this phi 0, this is given by this bubble, right? By this bubble and the process 0, which is the equation for the heat equation. And in the bubble tower, this phi is determined by the interaction between different bubbles. Okay, so we linearize, right? Linearize and the problem, but this linearization doesn't give us estimate. So in the talks we use in the talks in the last 3 talks we use the inner green. In last talk to consider blob solution with bubbling behavior. So here we take a reversed view. We already have a solution, and we decompose our solution into inner part and outer part. Okay, this is different. The inner outer green to construct a solution, we construct the error by decomposing the solution into inner part and outer part. But here we already have a solution. We already know the error. So now we have to decompose the error into the inner part and the outer part. Okay? So the inner part satisfies the linearized equation around the standard bubble. The outer part satisfies a parabolic equation with a small Hyder terms. And we have to see how these two terms, the outer and the inner, they interplay. And so there's a closed loop feedback between the inner and outer components. So let's look at one bubble. So the one bubble, this is the Orban tangent bubble, which you mentioned many times. And we know it's non-degenerate, and we know the kernel. And by the tangent plane analysis, we have this decomposition of the measure, and so we can decompose the u in this Orban tangent. So we can assume that this lambda I is the maximum of u at the maximum point. Okay, and we can do a decomposition. We found the best one. We can find the best one, and we also need to decompose our u to the unstable direction, because the unstable direction gives you the instability. So we have to decompose u in the unstable direction. So now we take a cutoff function lambda I k. K is the R. K is the R. And and uh, and and we look at the problem, the the error function for the inner problem. The error function for the inner problem, we want to look at where in k lambda. The error function in the problem is the linearized problem, and with the dynamics with a lot of a prime, kappa prime, lambda prime for high order terms. Now, these terms are where we don't have any regularity. So this regularity will come from the phi. So, and we need to get the estimate for phi and the estimate for AI, estimate for kappa I prime, estimate for lambda I prime at the same time. Okay, and so we need the at the same time we should get an estimate for phi I and estimate for lambda I. Now, so what we're doing is the reverse way. We assume we already have a solution. We decompose into the inner part and the outer part. And for the inner part, we need to get up here estimates at the same time get the dynamics. So this is our cutoff. We take this cutoff. So we take the inner solution as 8i cut in k, and the outer solution is 1 minus eta you cut in L. So the inner outer will have an overlapping regime in between L and K. So this is how we define the inner problem and the outer problem. Now let's analyze the inner problem, analyze the outer problem. So here we're not constructing solution, we're analyzing the solution using the green. Okay. And we for the inner problem, we can estimate the inner problem in terms of the outer problem by a small number A. This is the outer region. And for the outer problem, we can estimate the outer problem by the inner problem by some number B. And the inner outer green mechanism works if these two constant multiply is less than 1. And the main reason is the fast decay estimate from the bubble domains, which we mainly rely on a Gaussian bound on Hyder kernels associated to a parabolic operator with a small Hardy term. So this is the reverse in the outer now. Reverse in the outer problem. Okay, so for the inner problem, with those as in the construction, we have the inner variable tau, we have the inner variable y, and we have this inner equation, we have this orthogonality condition, and because of the non-degeneracy condition, and 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 we get the exponential in tau, and this part, it turns out that because I already have the I already have the L2 orthogonality with structure Ci. This part does not enter into the this estimate for phi k. So because I don't know A prime, I don't know kappa prime, I don't know lambda prime. Okay, at first I don't know this dynamics. And it turns out this is like the Lagrange multiplier. The Lagrange multiplier never enter into the estimate for phi for the inner problem. Okay, and so we under the outer problem for the outer problem we have a linear heat equation, but we have a lot of Hardy terms, lot of small Hardy terms. Okay, because the Hardy terms is like delta over x minus cos I square. Okay, so we need to know, and we have the cutoff terms from the inner to outer. Okay. Now for the outer problem, we have the following key heat candle estimate, and this is a very useful heat candle estimate. It says that if as long as your Hardy term, the coefficient of your Hardy term is small, you can have a very good estimate for the heat kernel. And this gives us the decay estimate for the outer problem. And so this is a key estimate, and this is obtained by Sanoff and Costa and Mossini and Tessie. So, and using this, and so the outer problem consists of more than 3 terms. One with the Cauchy differential problem, the differential problem, and also the inner the cutoff function from inner and the outer, and also the dynamics, and so the fast decay gives us a small transmission coefficient to inner to outer, which close our estimate on phi I. Okay, so we have this, and then by local partial density, we'll get, because we have just one bubble, we get the dynamics for lambda and dynamics for psi, and we get the type 2 cannot happen. And this is one bubble case. And this one bubble case, we get the dynamics. And from this dynamics, we say the type 1 cannot happen. So what about the multiple bubbles? What about the multiple bubbles? First, we show that the bubble towers are unstable. So, and if we have a bubble tower, and we can still localize in the neck region, and we do this estimate, and then we estimate the interaction between the bubbles, and the interaction is positive, which means the bubbles are repulsive. The bubbles are repulsive, so which means that the bubble tower are unstable, and for the bubble cluster, the proof is very complicated because we have to do different groups. We have to do a bubble tree argument and decompose the bubbles into big bubbles and small bubbles. We analyze the group interaction between bubbles and do the proof. So since the whole computation is very complicated, but in the end you can show that the bubble cluster is also unstable. So and this proves the theorem that for n greater than 7, there are no type 2 blob. Okay, all possible solutions, all blobs are type 1. So in these 2 lectures, I discuss is a very condensed lecture. It's not condensed lot of techniques, and we discuss the L2 case, the non-L2 n greater 5, the non-L2 case, and the 2, 3, 4 in each dimension. We have to use a different technique. We have to use a different technique. And in the last part, I also discuss how we can use this gluing to analyze the blob, the singularity formation for parabolic problems. And I hope all this will be useful when you do singularity analysis, or you are going to construct solutions, and so on. And the next time, tomorrow, I will move to the Euler equation. Okay, that's for today. Thank you.
Okay, so thank you for the nice talk. So I have one small question, like in lower dimension 3 and 4, because of
Yeah.
the building block, you use the positive bubbles, and the slow decay was a big issue. Now, if you use
Yeah.
then would that be better? Because in you
Very nice question. Okay. I tell you that there's one paper on Schrodinger equation in dimension three, and and uh, this is a paper in JFA, and they use the sun change bubble. So the sun change bubble has a fast decay, will be L2, but unfortunately, we compute the kernel of the sun change bubble. There's one kernel which is not L2. So the solution is L2. But there's one kernel which corresponds to the Carry transform. That kernel is not L2. And this is a big problem. Again, is you cannot you have to combine both L2 and the non most of the kernel are in L2. There's only one kernel which is not L2.
okay. So any other question?
So maybe I'm thinking more from the elliptic perspective. So
Yeah.
basically, I think to rule out this multiple configuration, you kind of show that they are unstable. So in the elliptic case, we get better and better improved estimates of the blow up sequence by the bubble. We improve it, and then we show that it cannot come too close. So does it play the same role when you are proving that the any multi-bubble configuration, whether it is clustering or towering, is unstable?
Okay. I think that the stability for elliptic problem and the stability for the parabolic problems are different. So I would say the stability for the parabolic problem is means that they cannot survive when T goes to capital T. These two structure. Basically, they just repel and they don't survive. Now, for the elliptic problem, the stability is more in the perturbation of the coefficients or this, right? There is a different definition. But I believe the analysis, the analysis we're doing here, which is doing the bubble decomposition and the bubble this bubble tower decomposition, I think this is we borrow some idea from the elliptic. Yeah, we
So
borrow
maybe,
some idea from the
yeah. So
elliptic.
maybe what I wanted to ask is, like in the elliptic case for the compactness arguments, what you typically, I think it goes by is you want to show that 2 points cannot come very close to one another because they can be approximated very well by improve derivatives of the bubble, right? So for the compactness argument, but here you are kind of using this proving that this kind of configuration is unstable. Is it related? That's
Yeah,
why.
in the elliptic case, you use partial mass to exclude the bubble cluster, right? Or
Yes.
bubble tower,
Yeah,
right?
anything
You
such
use
cannot
partial
happen.
mass. But here we don't have partial mass. Here we
Okay.
use the dynamics to exclude.
Okay. And
Yeah.
okay. And when you reduce it to finally one bubble case, again, is it like maybe I'm thinking everything in elliptic perspective, use something like maybe like a positive mass theorem or something like that. But here it's not coming into the picture.
Uh, yeah, this is a very nice question. And here we don't have partial mass, but we have
Because it's
the
flat, everything is
ODE.
flat. Ah, okay.
This one, it comes from this one.
Okay. And then again, maybe in lower dimension, probably suitable lower dimension where you have the right decay, can you still get something like that the points they need to be separated? You cannot have clustering or towering.
The problem is that for lower dimension, we don't. I think that we don't know how to get the next order estimate
Okay.
because the next order decays 1 over r to the n minus 2. So your solution will be 1 over r to the n minus 4. And you want this one to be L2
Yes.
because you want to include this next order in your computation. And this is for dimension 5 and 6, we don't know how to do this. But in the regional symmetry case, we can do it. In the regional symmetry case, we don't need, the main problem is the bubble cluster.
Yes.
The bubble cluster, yeah.
Thank you.
So any more question? Any question from the online audience? Okay, looks no. So let's thank the speaker again.
Okay, thank you, and hope to see you tomorrow. Thank you very much.